Good morning, everyone. Myself, Dr. Akshay, working as an assistant professor in VNR VJIT. So today we'll discuss about one of the important topic that is called as a servo and regulatory control under a process control instrumentation course. So basically, when we discuss about the closed loop control system diagram, we can see this is the closed loop control system diagram. Now, if you compare this particular diagram with open loop, we can find out additional thing here, that is the feedback. So let's say I have a measuring device here in feedback loop. So consider YSP, this is the set point, or this is the reference signal. Say the measured value that we are getting from the sensor, consider it is having a signal YM, whereas the set point is YSP. The difference between the set point and measured value is the error, and that error is given here. This error is a signal which is given to the controller. So controller has to modify error such that the output has to reach the set point. So consider the transfer function which is shown here for a controller, or say it's having a gain GC. Then the controller output, that is CO in percentage. This controller output is given to final control element. So in this diagram, so the final control element is represented as a GF, that is the gain of the final control element. The output of the final control element, that is a manipulated variable MV, it is given to process. So in this case, our aim is to control this process under normal operating states as well as in presence of the disturbances also. So so let's say we are introducing a disturbance to understand the effect of controller in presence of disturbances. So how the controller is going to perform in presence of load or disturbances, that we need to analyze. Consider this GD, this is the disturbance gain. Now the control variable or the output of the process is given as a Y. So what exactly this servo and regulator operation consists of, or we can say the set point tracking and disturbance rejection. So if we consider one example, let's say we'll plot a response. So consider we are giving some set point. So for example, I have given here a set point, right? Now for the set point, what is the expectation from a controller? We know that in control systems that the controller should change the output such that it will reach the set point variable. So as soon as we are given some output, let's say slowly, or the set point is given, slowly the output is changing, and after some time it should reach the set point. So let's say at T1 we have changed the set point. So let's say we are giving a new set point. Now what is the desired response or the expected response? The controller should make changes in manipulated variable such that again the output variable should reach the new set point value. So slowly the output is changing and it is reaching the new set point. Consider at point or time T2, again we have changed the set point, and consider the new set point is this one. So the expectation is that again the output of the system should change and it should reach, or it should reach the new set point. So basically whenever the set point is changed, the expectation is that the controller should make the changes such that the output should reach the new set point. So basically this is called as a set point tracking problem. Or if we consider servo mechanism where angular velocity or angular position has to be controlled, so in that case we can consider it as a servo operation. For example, position control of a robotic arm with the help of say servo motors, or controlling speed of a servo motor. So those can be for different set points or for the different trajectories. So that is one example of servo operation. Now coming to the second part, that is called as a disturbance rejection. So if you see this closed loop control system diagram, here we can find the process is also getting affected by another input, that is undesired input called as a disturbance variable. So now what is the expectation from a controller or from a good control system? So let's say with respect to time t, now we are not changing the set point, because now the set point, let's say it is 0 or it is a constant. Now when my set point is constant, the expectation from the control is that in presence of disturbances also, as long as set point is constant, so output should remain constant. So for example, now let's say there is no disturbance applied, so I will consider here some small disturbance signal. So let's say at t equal to 0, no disturbance present, so the output of the system is changing and it will reach, let's say, set point. Now consider at some time t1, right, a small disturbance or disturbance is introduced. So for example, if you consider a liquid level control, say the output flow has been suddenly changed, or let's say if you consider a temperature control, say the suddenly the surrounding conditions has been changed, like ambient temperature has been changed. So now as soon as the disturbance arises, so expectation is that now in presence of disturbance, the output of the system may change because of the presence of disturbance. Let's say in this case the output has decreased. The expectation from the control is that for this or in presence of the disturbance, now the output of the process has been changed and it is deviating away from the set point. So the expectation is that controller should make changes in manipulated variable such that again the output should reach to the set point variable. So again you can consider that, let's say at time t2, again some disturbance is introduced. Now till this t2, the output was maintained constant at set point. Now at t2 again the disturbance occurred. Because of that, the output will fluctuate and it will go away from the set point. So in that case, the expectation is that again the controller should change it back or change the manipulated variable so that it should come back to the set point variable. So minimizing the effect of disturbance so that the output should stay at set point. This is what called as a regulatory operation, or we can say the minimizing the effect of disturbance. So if we consider some examples of servo mechanism, let's say we need to maintain the position of a robotic arm constant, or let's say some we can say some load or some object is there and we need to maintain its position constant in presence of disturbances also. Say antenna position we need to maintain constant. So in that case we can go with the regulatory operation or disturbance rejection. So if we see this particular closed loop control system diagram, now we'll try to understand from the transfer function model how exactly controller plays very important role to maintain servo as well as a regulatory operation, or we can say it will maintain the set point. It will maintain the output at the set point as well as in presence of the disturbances also. It will try to maintain the output at set point as long as set point is a constant. So if we consider this closed loop control system diagram, and from that if we derive the equation for output for the two different conditions. Condition 1, in this case, let's say disturbance variable d of s is 0. In that case, we'll get the closed loop transfer function, that is nothing but we have GC for the controller gain, GF is the final control element gain, process gain is GP. We have measuring variable or the measuring device gain is a GM. Input given to the system is YSP, whereas output of the system is a Y. So if we go for the transfer function for this particular case, when disturbance is absent and we have applied the input, that is a set point. So we'll get the equation that is for the output Y of S divided by input, that is a set point ISP of S. We'll get GP of S, GF of S and GC of S divided by 1 plus, this is like a g of s divided by g of s into h of s. So divided by gp of s, gf of s, gc of s into measuring device gain, that is the gm of s. If we simplify the equation, we can get the equation in terms of y of s is equal to gp of s into gf of s into gc of s divided by 1 plus gp of s, gf of s, gc of s, gm of s multiply by set point variable ysp of s. So now what is the expectation in set point tracking? This output variable, this is the output and this is the desired input. So output must follow the changes in the input. So if you see this transfer function part, so in this gain of the process, gp of s will remain constant. Feedback element gm of s, the gain will remain constant. Final control element, its gain will remain constant. So we have one parameter, that is a gc of s. And if you see the even characteristic equation, if I read here, if I write the characteristic equation 1 plus say gp of s into gf of s, gc of s and gm of s, this is equal to 0. This is the characteristic equation. So in this characteristic equation, we can see the parameter which can be varied by the control engineer or the operator is gc of s. So the selection of gcs is gc of s, there is a controller gain is very crucial, whether we need to select proportional controller, pi controller and the controller parameters like proportional gain or integral time. It is very crucial in set point tracking performance. Now if we consider the second part, that is for the disturbance rejection. So now let's say the set point is constant. Now I will consider the set point, say ysp. Let's say ysp of s is a 0 or let's say it is a constant. So in that condition, from the closed loop control system diagram, now our input is disturbance variable d of s. Now in presence of a disturbance, so how the controller is going to make the output to stay at set point, it is very important as far as disturbance rejection performance is required. So consider ysp, that is a set point is a constant. So in that case, if we consider the input as a d of s and now the output is y of s divided by, now in this case input is disturbance variable d of s. So after simplifying or from the closed loop control system diagram, we will get this is gd of s, this is the disturbance gain divided by gp of s into gf of s into gc of s into gm of s. So if we rewrite the equation in terms of output, so we'll get this as a gd of s divided by 1 plus gp of s, gf of s, gc of s and gm of s, and this multiply by disturbance variable d of s. Now we don't want that output should be changed due to d of s. So requirement is to minimize the effect of this disturbance. So again, if we see the characteristic equation 1 plus this, I'm writing here the characteristic equation. If you see the characteristic equation, you will find out again as gm of s, there is a gain of the feedback element of the sensor device is constant. G of s, that is the feedback control element gain is constant. GP of s, process gain is constant. So operator or design engineer have a choice to change GC of s, that is a selection of either P controller, PI controller, and the most important thing, what should be the value of proportional gain or integral time. This is very crucial to minimize the effect of disturbance, right? So as long as set point is constant, we want the output should also remain constant. So performance of controller for set point tracking as well as disturbance rejection is mainly depends on what type of controller we have selected as well as the controller parameters. Now if you write the set point tracking part, there is gain of the set point element. We can consider GSP for this entire part. and the second thing is the load gain or the gain in presence of disturbance. This can be the part. So we can write a simplified equation for overall equation for output, that is GSP of S into set point YSP of S plus disturbance gain into disturbance variable. So in both cases we can see the controller plays the most important role. So we'll see with example how exactly we can study effect of controllers for set point tracking as well as disturbance injection performance. So as I said earlier, we can see here the effect of when we considered here the both cases. So the first one is set point tracking, and the second case is for disturbance ejection. So in both the cases you can just check. For the first case, again I will revise before we see the practical example how set point tracking uh, as well as disturbance ejection performance, it mainly depends on the controller gain. So if you consider the what exactly set point tracking means, so in this case you can see that the set point is changed. Initially it is at 0, then it has been changed to 3, again it is brought back to uh, 0, again it has been changed to 4, and again it has been brought back to the 2. So here the first set point change, again set point is changed here, again set point is changed here. So somewhere around 60 seconds, again at 90 seconds set point has been changed, and again around 120 seconds set point has been changed. So whenever set point has been changed, you can see here the blue colored response, that is for the set point, and the black color, it represents the output variable. So you can see here the controller is bringing back to the output, and it is trying to maintain at set point. So whenever we are changing the set point, the expectation from the controller is to maintain or to bring that output at the set point, and to maintain the output at the set point region. So this is the set point trajectory, and we can see here the output is following the set point trajectory and staying there as long as the set point is not changed. So if you consider the second diagram, that is for the disturbance rejection, or we can say in a regulatory operation. In this case you can see the set point is constant. So for this case set point is 1. The expectation is that as long as set point is constant, is 1, the output, right? So you can see here the reference signal is given by blue line, and the change in the output, so that is given by theta. So let's say the set point is 1, and the expectation is that in presence of disturbances also the output should remain at set point. So you can see at 50 seconds some disturbance has been introduced. So there is a deviation of output that from the set point. So immediately you can see the controller is bringing back the output at the set point, and it is maintained. Again you can see around 100 seconds, let's say, again the disturbance is introduced. So you can check it here that immediately the output is brought back to the set point. So this is what we can say the disturbance ejection or a regulatory operation. So we'll see now some examples where we can apply this servo mechanism. So you can see this is the example of solar tracking system. So what is exactly the servo mechanism or set point tracking, that we can understand from this particular example. So we'll see first this example. So in this solar tracking mechanism, we can see here there is a solar panel, right? So we have a solar panel. This is solar panel, right? So what is the objective? Now you can see the position of the sun, right? So as earth is rotating, so the requirement is that always the solar panel must face the solar what you call the sun, towards the sun. So always the face of the solar panel should be towards the sun. So we can see the set point is we can say the angular position, which is continuously changing. So the requirement is that to use some control mechanisms, so that always the controller will make the solar panel towards the sun, so that optimum solar energy can be collected. So how it can be done? So you can see this control system mechanism. So here what is done, the set point is what, the angular position, and depend on the angular position always the solar panel should be towards the sun. So here we need to use some electric drive. So for example, if we are using a servo motor, so on a servo motor we can fix the solar panel with the help of a gear assembly. So you can see it here how exactly it can be fixed. So you can just check it. This is the motor. So let's say this is the servo motor. On the servo motor shaft we can have the gear mechanism. For example, so let's say this is the shaft. This is the shaft. Over this particular shaft, let's say this is one gear assembly. To this first gear assembly, let's say another gear is engaged. To this gear, let's say one more gear is engaged, and on the last on the last gear assembly, let's say we are going to fix some load. So let's say this may be robotic arm position or some object whose position or the angular position we need to maintain. So we can have this gear transmission ratio, so that angular velocity can be converted in terms of angular position with the help of the gear transmission mechanism. So in this case you can see that the first thing is that the robotic arm, for example, the arm position can be detected by using some sort of position sensors, like either it can be a potentiometers, which is shown in this diagram, or we can use position encoders, and that will give the information about the present position of the it may be antenna, it may be solar panel, it can be a robotic arm, to the first controller, that is you can say the position controller. Then as we know that by changing the speed of, so to change the speed of the motor, or we can say the torque, it is proportional to armature current Ia if it is armature control motor. So by changing the armature current we can easily change the torque of the motor. So to change the speed we can make the changes in either VA, that is armature current, or armature voltage. So the first one is the position control. Another feedback also we are taking, say with the help of tachometers we are continuously monitoring what is the speed. So what can be done? So to the speed control mechanism we can give the new set point every time. That is nothing but what is the present position, what is the required position, the error of that will tell what should be the new position, so that the output will reach the required set point position. So that correction will be done. So for that we require to know the present speed of that particular motor. So the output of the speed control mechanism, that is given to a power drive, and that will give the current Ia to the armature windings of the motor. So in this case, let's say aim is to maintain the position of, say, robotic arm, one example, or we can say we need to control speed of a DC servo motor. Thereby we can make changes in, say, the position of solar panel. So in short, you can remember, for servo operation aim is to maintain output at set point, whereas for regulatory problem, as long as set point is constant, requirement is to maintain output at set point value. So controller must minimize the effect of disturbance to maintain output at set point variable. So from the characteristic equations for servo as well as a regulatory problem, we can see that the controller performance for servo as well as a regulatory control applications, it mainly depends on what type of controller we have selected, as well as what are the controller parameters. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.